There we go. Cool. Okay, so today we're going to talk a little bit about how networking actually works, because it's one of the things your operating system takes care of for you. It manages all of the things connecting your computer to all the other computers on the internet. And as programmers, this is one of the areas that we're going to get involved with more and more. And so it pays to know exactly how the internet actually functions and behaves. And recognize that, early on, networks were kind of an afterthought. They were things that were bolted together, that were proprietary between two machines that were identical. And it wasn't until Unix was invented in the 70s that Kernighan and Ritchie integrated networking and network protocols into the operating system, and we were able to universally get different applications to be able to talk to each other. And part of that was put together because of the way that they devised for internet addresses to work and how each computer can access each of the individual things that they need to communicate from one to the other. We'll dive into how once we can connect two machines together, we send information back and forth. And we try and leverage a lot of the things we already know with how software works and how we can use the way we read and write data in and out of our applications directly to the operating system to kind of redirect these things to different locations. And finally, we'll talk a little bit about distributed computing and cloud computing and what's really different about them and how we can use them. Ultimately, our goal here is for you to be comfortable enough that by midway through the program, you feel like you could, in fact, write a networked application, and that it's not scary, that you understand how it functions, and certainly we'll be doing a bunch of asynchronous communication with networks and network servers while we're here. This is kind of the route that most future applications are taking these days. The client side, the game side that you operate in, is a very small piece of what really goes on. So we'll start with just how distributed networks work. Now, it all starts from the premise that you have an interconnected network of computers. And when we mean interconnected, we mean we've got the physical connection to allow us to talk between two machines. And that's really what we're talking about when we're talking about the internet. The internet itself is a collection of wires. There's nothing fancy or special about it. How the internet really works really comes down to how are the machines interconnected with each other. And that largely comes down to one main issue, which is how do I talk to another machine? How do I physically say that guy over there? Some of you may have seen some of this stuff before, certainly heard about certain aspects as you've played games or worked on things. But when we're talking about those addresses, we're talking about an internet address or an IP address, an internet protocol address. And those addresses uniquely identify a computer on the network. Where things get complicated is that if it's at all possible to realize how big the internet is, there are not enough addresses to go around. And so what do we do when we have to address something, but we don't have enough addresses to go around? The other thing we have to deal with is once we uniquely identify the computer that we want to talk to, that isn't enough for us to be able to connect to it. Remember, our operating system is running multiple different programs. So we have to have some way to figure out which program are we going to talk to. And to do that, we're going to combine a couple things together. we're going to combine an internet address with what we call a port number. Now, for the internet addresses, these numbers are typically expressed in terms of hexadecimal or octets, and they're 4 groups. Now, this is what we call IPv4 network addressing. And it's the standard IP address you've seen all along. It has 4 numbers from 0 to 255, separated by a period. And they're collected together in groups. And the whole idea of collecting them together in groups is that you could create sub-networks if you need to, so that you can map a single address into a collection of other addresses. This is definitely what happens at your home. If you've ever played around with your home, there are some predefined network subdomains, if you will. The 192.168 subdomain that you set up with your home networking is an alias for all of the machines inside your home network. From the outside world, it appears as if it's a single machine. Inside your home, it could be any number of machines, up to and including 255 groups of 255 machines. If you look at Electronic Arts, if you looked at Google, if you looked at VFS, from outside, they appear as if they're a single machine. If you try and find out what Google's internet address, you'll find one address. But it's pretty safe to say that VFS, Google, and any other company you might connect to has more than one computer connected. So at some point, we need to redistribute what we're doing. We need to connect to the main connection point in that organization and reroute from that main organized computer to another set of computers, or remap where we're going to. And once we get to that destination computer, we're going to need to figure out which program we want to connect to. And that we're going to do through a port number. So those 2 components are what we use to uniquely identify a destination we want to talk to. An IP address and a port number. And there's 65,000 port numbers. There's a really large number of IP addresses. And there's also some default addresses and port numbers that have been set aside for general purpose use, for testing, for different applications, and for default or conventional type apps. And once we connect these 2 computers together, we have just started to work on the networking side of things. This is all managed by the operating system. But once we connect the 2 machines together, we have to figure out how those 2 machines are going to talk to each other. And this comes down to the fact that each computer is going to send a collection of bytes from one place to another. And it's up to the receiver to figure out how to reassemble or disassemble those bytes into something useful or usable. That communication, the what do we send between the computers, that is typically called what we call a protocol. Now, a protocol is not software. A protocol is not a library. It's not a specific tool. It's a specification. It's the language that allows things to talk to each other. It makes people able to communicate with each other because they're both talking the same language. The group, International Organization Standards, that sets up these protocols is called the IEEE, or the International Electrical and Electronics Engineers Association. And they meet as a group with representatives from all major companies on a very frequent basis and review all of the upcoming new technologies and review all of the existing protocols and standards and try and see if they need to update them. The major protocol that we talk when we're talking about internet connectivity is what we call the Open Systems Interconnect Protocol. And this is the one we're interested in understanding how it works, and at a very high level, being able to flip a couple switches in our software libraries to be able to manipulate it. That protocol layer identifies specifically how information from one computer, that data structure, that collection of bytes that you want to send from your computer and your program to another computer and another program, how does it get from A to B? And this OSI protocol stack looks a little bit like this. If you look at the stack, you start at the bottom and move up. So we go down from the sender and we hit the bottom. It goes through the physical wires and comes back up through the same protocol stack at the receiver. Now I'm kind of in front of it now. I'm going to dive out of the way for a sec and let you take a look at how this actually works. So if you can picture your data, a chunk of information you want to send from your computer to another one, that's your application layer. That's your data. So we're just going to call that the payload. That's the collection of bytes we want to send. We then pass that into a presentation layer. And in this case, we add a header. It defines the kind of data we want. Typically, it's either binary data, some bytes, or it's textual data, some text information. This is managed by an operating system library. You link in the library that the operating system provides, and it gives you the tools to present your information and prepare it to be sent somewhere. From there, you make another library call to send it into what we call the session layer. And this is the part that adds another header that tells us the style in which we're going to send our information to the destination. Now, there's a lot of different header information styles, from SQL information to remote procedure calls to web protocols to network file system protocols. And all of these try and tell the receiver how to interpret the data it's going to get at the far end. This information gets passed into your network hardware in your computer. This is referred to as the transport layer. And we're really just flipping a switch here. And we're going to talk more about this switch we flip. The switch we flip determines whether we're going to send this information using a specific protocol called TCP or UDP. You have a choice. It's one or the other, not both. TCP is the transport protocol for network packets. UDP is the unstructured data protocol. Now, those two individual protocols have things about them that we take advantage of when we're sending our information back and forth. The transport protocol has this nice property of guaranteeing that your entire payload is going to get broken into pieces, and each of those pieces is going to get sent to the same destination, and the transport protocol is going to guarantee that every piece of information, every packet arrives, that they get ordered in sequence, and that if a packet somehow fails to make it through the network, the sender will resend the packet until it gets through. That means you're guaranteed your information makes it there. And you're guaranteed that it gets there in order. UDP, on the other hand, takes all of those constraints away. It says, just take a chunk of bytes, break it into a bunch of pieces, shotgun it through the internet, and hopefully they'll all arrive at the right place. But we're not going to guarantee it. And there's different advantages and disadvantages to each. Now, that happens inside the network card or the network interface controller, or NIC, inside your PC. That information that gets passed out of that network wire, and it gets sent to a local network layer, which happens inside the networking hardware attached to your personal network. That's your switch or your router. That information now has information on the IP address and port number of the destination. And so that logical addressing gets appended to the end of your data. We then take that information and run it through some firmware to add all of the information we need to break every chunk of data into nice logical packets. Each of those packets is going to be scaled size-wise to go through the internet very quickly. We're talking about things in the neighborhood of about 2K or 4K. In order to make sure that they arrive at the destination and are exactly the same as where they left, we're going to add what we call a cyclic redundancy check. We're going to add a code to the end, which when run through some math is going to take a look at the data and make sure that the data received is the data we got and the data we sent. All of that is then packaged up and bundled into a stream of bits, ones and zeros. And those ones and zeros get fired out onto the internet wire as a series of positive and negative plus 5 volt, minus 5 volt signals on a square wave across the internet. Now, all of those pieces of information are important because when we start routing our information, we have to figure out where each step, each packet is going to make along the way. And at each step, we're going to take that physical information and we're going to decode it into that data link information, and we're going to decode it into the network packet, and we're going to see if the address is my address as a receiver, and if it's not, I have to figure out where to route it to next, and then package it back up and route it to its next destination. If it is my address, then I know it's for me, and I can pass it up into the operating system where the transport layer can start to decode it and figure out what part of the application to send it to. Now, if that's a little hard to wrap your head around, the easiest part to remember is you don't have to deal with 90% of this. Everything in the bottom box there is handled by the network hardware in your network. The middle box is handled by the network interface controller card in your PC. There's software written onto those things to help encode and decode information. The last 3 layers are all taken care of in your application. And in your application, 2 of those 3 layers are handled by a network library that you link into your application. So all you really have to do is figure out what's the information I want to send from A to B, and what's the magic incantation of function calls I need to make sure my information gets packaged up and sent off to the right destination in the right format. On the receiving end, if you're running the server side, the part that receives information, all you have to do is figure out what kind of connections you're going to allow, set up a server to wait for and listen for these connections, and when you get them and you get information from them, how do you decode it? Right? Now, all of your data is broken into all of these layers for every packet of information. And how big the packets are, you don't have any control over. Okay? That disassemble and reassemble of stuff, in terms of putting all the packets back together again, is something that that TCP layer does for you. In the bottom layers, that's all done by hardware that's in your network. So, the parts of your network that do all of this are these typically small pieces of equipment that are run by essentially programmable logic controllers. Switches, routers, firewalls, these days are very, very similar. In fact, they're all pretty much based on the same hardware. Technically speaking, switches are dumb. Switches simply route one thing to another place. And you all have basic switches on the desks in front of you there, where they have multiple different network wires coming into them, and one of them goes to your computer. if you were to send information from your computer to the one next to you, the information would go through the protocol stack. It would go into the switch. The switch would go, oh, the IP address you're looking for is on this output port, and it would send it to that output port, where on the receiving computer, it would come back up through the protocol stack, disassemble all those headers, and deliver your data back to your appropriate application. All of that without ever going out to the internet. So this is what the switch does for us, is it tries to route things locally. Now, if it can't find the IP address you're looking for locally, it has to do something with it. So the switch is smart enough to hand your information up to the next higher level switch. You can think of it as a tree structure. And as you hand things up, each tree has a routing table to say, hey, everything I know about is on this set of ports or network connections out. And everything I don't know about goes to this one connection, which is technically referred to as our gateway. Now, routers are smart. Routers are what we normally have these days on our desks. They're switches that have memory. And what we mean by that is that routers, as long as they're on, keep track of connections that are directly linked to them. And whenever they start to see traffic patterns, they will instead try and reroute things quickly. So they will start to keep network switches or network routes that are used frequently in their memory. And by this mechanism, they can more quickly route things from one place to the other. Hardware firewalls are exactly like routers, except they get in the way when you try and access something that has been blocked by the firewall. So the firewall says either this IP address or this port number or range of port numbers is inaccessible. And most corporations employ some sort of hardware firewall to either prevent people from the outside seeing certain things on the inside, or in rare cases, VFS being one of them, that prevents people inside from seeing certain things outside. So, for instance, one time, one student decided to stream Netflix to a projector. Therefore, VFS IT blocked all of the Netflix ports coming into VFS on their firewall. So you should not be able to stream those things again. And the logic there was, we're paying money for bandwidth onto the internet. We don't want to consume all of that bandwidth so that students can't work by one student who's streaming a large media file. So in this way, we can build up hardware that helps us protect our network. All of this means we need to navigate through this maze of hardware and software if we want to send information from one place to the other. Those libraries that your operating system uses, those libraries need some information to start from. And that information we start from is typically our IP addresses and port numbers. So here's the way they actually look. An IP address typically identifies a machine uniquely within a subnet or a subdomain. So underneath a switch. On each computer, you have a number of port numbers. And each port number can be associated with a program. So on your Windows computer, there's an internet service. And the internet service maps port numbers to applications. So that if somebody tries to connect to your machine's IP address and port number 8080, port number 8080 in the internet service on your computer is mapped to a web server. So when someone tries to connect to your computer's port 8080, that connection is routed to the internet service, and the internet service starts up the web server to answer that request. Those two things are connected together, and once they're connected together, software-wise, then they're allowed to pass chunks of information back and forth to each other. Now, the problem with our typical IP addressing scheme is it only allows for about 4 trillion unique addresses. And there's more computers and devices on the planet than that. So lately, what's been rolling out throughout the internet is what we call IPv6 internet addressing. And if you want to see what these things are, bring yourself up a terminal. Now go to your start menu and type CMD. Let's see if I can. See if I can find a way to do this. Oh, yeah. There we go. So there's my command prompt. Just scale that a little bit and throw myself back in there. So when we look at our command prompt and we want to look at the network aspect, just type the old ipconfig file. ifconfig is the equivalent on a Unix machine. And if I scroll through here, what I see is the internet connection on my computer. First of all, I can see the domain host. That's the connection DNX suffix, which for you guys will be on BFS's network. Here you can see I'm on Shaw Cable's network. The IPv6 addresses you can see here. These are larger addresses to be able to have a larger collection of computers on the internet. What we get interested in is the IPv4 address. That's this guy right here. That IPv4 address is a local address relative to my switch. And I have this thing called a subnet mask, and you will as well. And the way these masks work is we do some math on these IP addresses. So if we AND them together or OR them together, we get different results. In this case, we AND them together. Now, 255 is representative of an 8-bit number, or 8 single bits. And the way those 8 single bits mask off different parts of that other IP address, they hide things from us. So if I'm looking at 192 and I AND it with 255, then I'm going to get 192 back again. I'm going to get 1 and 1 is 1. 1 and 0 is 0. And see if I can kind of scribble this together so that it makes a little bit of sense. Turn this guy on. Let's see. So if I take a look at this guy, and if I take that 255 and look at it binary, it looks like this. Now, 192 in binary, you can't see the drawing. No, you can't. Let me see if I can make it a little bit easier. Oh, that's going to be pain. Hang on a sec. Let me see if I can make this work. All right, let's see. Let's see if that's going to work. Yay! Eight bits. Yay! Now, let's see if I can't do this. So, let's choose this guy. So if I were to represent 192 in binary, it's this. Right? And if we use AND as an operator, 1 and 1 is 1. 1 and 1 is 1. 1 and 0 is 0. Right? Using the AND operator. So these are all going to come out as zeros. Okay, so all this craziness just preserves this number. So this mask right here says preserve the first, second, and third octets, and the third one we don't. What that's telling us to do in here, it means that when we look at this from a network address, it's only going to pay attention to the last digit in the IPv4 address. This is machine number 9 in my local address. Everything else gets ignored because this mask hides it. Which means anytime we have an IP address we're trying to connect to that's outside of this range, this 192.168.1 range, we have to let our switch have an idea of where to send it. And where do we send it? Well, we send it to the default gateway. Now, in this case, 1.1 is my default gateway. And on the gateway knows how to connect to the internet. So it will then identify any address it doesn't understand, any address that isn't a 192.168.1 address, and reroute it out onto the internet. Likely, if you looked at your host table for your network connection, in my case Shaw Cable, there's a specific domain name server that it can connect to. And that domain name server will have a routing table so that we can get the specifics of where we want to connect to. What the heck am I doing there? There we go. Shuffling around with monitors today. Now, what this means in practical terms is that we can break any network down into a collection of subnetworks just by injecting a switch in there. And when we inject the switch in there, anytime somebody tries to access the machine that we're on by accessing the switch's IP address, the switch is then responsible for mapping that address into another range. That's a router or a switch. That's its job. So if I want to connect to a certain IP address, like when you connected to the terminal that we were using to do the programming exercise in this class. That IP address you connected to was the actual external address of the switch on my home network. And when you connected to that switch, I had that switch configured so that an outside connection to that IP address was routed to a 192.168 address inside my network. So in this way, network switches can find and keep track of inside networks versus their gateway to the broader internet. You can expand this idea and get your idea for how networks route things. At this point, you can start to see how my device is sitting there on the left-hand side. Got all these things on the wrong side. Actually, let's do this. Whoop. So, my device sitting there is connected to a local area network. And that local area network has a bunch of different devices on it. And if you're connected via the Wi-Fi, you're connected over a radio communications channel directly to the switch or the router. And the reason the Wi-Fi is slower is in order to get reliability, they transmit things more slowly, and they transmit things multiple times to make sure that all the packets arrive at your router. And this is why your Wi-Fi connection is always in the order of 10 times slower than a wired connection. That router on your network, that block in the middle here that says local behind it, that has a gateway. That gateway is a single internet address that identifies the router in your internet service provider. That router in your internet service provider has access to what we call a domain name server. The domain name server is the thing that looks up, hey, google.com, what IP address is that? And it gives it an IP address back. If that IP address is connected to that ISP router, it just goes ahead and routes your information there. If it's not connected to that router, which it typically isn't, the router passes the information on to its gateway. And so on, and so on, and so on, until you get to what we call a top-level domain. Now, there's a collection of top-level domains. There's about 10 of them in total. They're managed by an organization that's a nonprofit called the INTERNIC, I-N-T-E-R-N-I-C. And if you were to register a domain name with a domain name service, you would then have to register it with the INTERNIC. Private individuals aren't allowed to do this. Corporations can. So if you go to GoDaddy and you want to get mydomainname.com, you submit a registration request to them and pay them a fee. They take mydomainname.com and they go look it up in the domain name servers. And they start by looking at the top-level domain.com. If they find that there's no mydomainname.com, they will then assign an IP address to that domain name, register it with the domain name server, that's a big lookup table, and hand you back a place to access your information. Typically, they'll carve off some space that you can remote into. That information in that top-level domain server is then percolated and propagated through all gateways and all routers in the internet, until we get to the point where all of the ISP routers know about it. Then, when you get on your device and you say, go to mydomainname.com, it goes to your local router. Your local router doesn't recognize it. It hands it to its gateway. The gateway hands it to the ISP router. The ISP router looks it up in the domain name service, grabs the actual IP address, and continues the routing process. Now, if you think about this, every single packet from your application client to your application server has to go through this process. Every single packet. which is why we bake a lot of the software that does this into the hardware. Hence that 7-layer protocol model. A lot of those layers baked directly into the hardware we're using. Does that make sense so far? I know it's kind of complicated to get through. Okay. Now, you got a general idea? The biggest thing to go away from is you got a rough idea how to connect one machine to another. You need an internet address and a port number. It's not rocket science. Every router works the same way. It has a 2D array. It has its gateway, and it has all of the outgoing pathways. So it knows a list of all the things that are connected to it, and it knows that if it can't find it in the list of things connected to it, it hands it up to another gateway above it. Right? You do have to trust that this network is maintained, so that if you want to connect from one device to another through the network, that by putting the IP address and port number into the information you're sending, that the network itself will route your information to its final destination. And it's probably pretty amazing that it does this typically in under 100 milliseconds. If you were to send a packet of information from where you sit today to a server in London, in the UK, it still takes only about 100 milliseconds to break your packet into pieces, attach the addressing information, send it out to your local router, which sends it to your ISP router, which sends it to the top-level domain, which routes it back into the server in London, and back into the ISP router in London, and back into a local router in London, and back to a local machine in London, where it delivers the information back up through the protocol stack. All of that handled by hardware. That is how the internet fits together. It's this giant connected web of routers. And they're all arranged in a tree-like hierarchy. Now, the top-level domains you've seen before. What are kind of the top-level domains you've seen? You've seen EDU. Those are United States education addresses. You've seen COM, which is the commercial addresses. You've seen NET, which is the nonprofit organizations that manage the network. And what else have you seen? Yeah. There's a collection of new ones, so not surprising.
Didn't Google just come up with this thing like Google domains where you can set it to basically whatever you want?
They'll redirect some of them. Right? What about .gov? It's the US government. Why the United States? Why would this be US-centric? It's a very good question.
The US military developed like the predecessor to the internet.
You got it. Originally developed by DARPANet, which was a US military research organization, to try and connect universities to the US military. And they were the guys that provided the funding for Kernighan and Ritchie to come up with their operating system and the internet protocol and the programming languages to go with it. As such, they gained ownership of it. The challenge they ran into is, in order to continue to fund it, they opened up the commercial internet. When they opened up the commercial internet, they kind of lost control of it. See, companies like AT&T would go and sell physical telephone lines from one city to the next and start putting their own routers in place. So now different companies could have presences on the internet, and the routing wouldn't necessarily go through the US military. And as these separate telecommunications companies started to put more and more infrastructure in place, more switches, more physical lines, there became more and more routes to get from one place to the next. And as long as the routers stayed interconnected correctly, everything just happily worked. So, for instance, the main internet trunks out of Vancouver go in two directions and two directions only. There's a main internet trunk from Vancouver to Calgary and another one from Vancouver to Seattle. And that's geographically speaking logical. That's where you'd put the wires. So when you send something to Chicago, does it go through Calgary or does it go through Seattle? And the answer is both, because we take the information you're going to send, we break it down into chunks, roughly 2K in size, and we fire some of them to Chicago, or some of them through Calgary, and some of them through Seattle. They all wind their way through these routers in the internet until they land at their destination, where they get reassembled in order. So at that point, DARPA kind of lost control of the internet. And so we now have direct control over what's going on there. Now, we're just going to be users here. We're just going to use the internet to connect one client application to what we call a server application, some remote location. And so understanding how this works can help us when things go wrong, but we kind of need to just trust that it's going to work. That once we send something out to an internet address with the correct port number, that it's magically going to find its way to that destination internet address, and that the port number is going to help us identify which program on that destination machine is going to be run to go and manage our data. So when you go and play Call of Duty, you connect to a server, right? That server is running somewhere, and typically the servers run in 3 locations. For Call of Duty, there's an office in Vancouver, an office in Ireland, and an office in New York, which means all of your Call of Duty requests got to be routed to one of those offices. West Coast, East Coast, Europe. And when your Call of Duty game connects to the server, hard-coded into the game is the IP address of something that's going to find one of your local servers. So you're going to send some information to the local server. What are you going to send? Hey, I'm Scott, and I'm logging into Call of Duty. Please go look up my account and validate my password. All right, let's take a short break. We're going to come back. We're going to talk a little bit more about some of this hardware, and then we're going to start getting into kind of the stuff we can actually affect. This was really just more a little bit of background on how the internet works. So I'm going to come back at 2 o'clock, and when I come back, we're going to talk a little bit more about network hardware and how we can take advantage of the way the network works to be able to set up 2 applications to talk to each other. All right?
you have public stuff. So, this is down this is a different, that's here, on review. And you want to review this stuff, this is for you want to go, okay, these are on the internet as well, on review as well. So, review, all over the world. And so, another one was, yeah, you're going to have to go to the app before you write code. What it is in something. This is the, nobody has one part. You're already reviewing stuff.
All right, let's take a quick look at some of this stuff before we can get to, actually playing around with it. So a little bit clearer picture of how our networking fits together would be to look at this kind of diagram where from the bottom up, we've got a bunch of computers that are connected through typically what we think of as a bridge to bridge into different networks, which we then connect to a hub, which connects a bunch of similar machines together, which connect to a switch, to a router. Okay, the reality is these devices are all just routers these days. They all have the full routing capability. Now, sometimes that's just not enough. Like if you're trying to connect to Google, for instance, how is Google able to make the physical distance from wherever you are in the world to Google servers seem pretty much the same? And the way they do this is they kind of replicate a few things. And the way they replicate them is they use what we talk about as what we call content delivery networks to replicate stuff. So Google runs one, Node runs one, Amazon runs one, Windows runs one. There's a bunch of private ones. If you have particular content that you want people to access, we put that content on a server, but sometimes that server is a long way away. So a lot of times we'll employ content delivery networks, which are really just software which auto-replicate the contents of a server in multiple locations. And we'll physically place the multiple locations close to where most consumers are. So if you purchase a content delivery network solution from Amazon because you've got some great game app that has a server that needs to be close to everybody, you get Amazon's CloudFront service and it takes your server and it copies it to 10 different servers around the world so that nobody has a really long ping time to get to your server. Your cloud-based server then can appear to be really close whenever you want to acquire information. That gives us a more complete picture. If we're particularly talking to web applications, we get this kind of picture from these top-level domains. From your machine, you're going to connect out to VFS's router, and VFS's router is going to connect out to the internet via its gateway, where we're going to look up things in a domain name server that's going to give us the closest content delivery network. That content delivery network is going to have a replicated version of our server or service, and that IP address is what's going to be handed back to us so that we can establish a connection between our client application and the final server or service we want to connect to. You can see this in practice. If you go to your command prompt and we type in the command traceroute, TRACERT, and just do something like google.com. If you do it on VFS machines, you'll get a really interesting result. It's going to sit there and spin for a little bit. And what it's going to do is it's going to try and connect to that end domain name, and it's going to do it by IP address, and it's going to do it one bit at a time as it maps out every server or router along the way. You notice mine is even timing out. It's taking so long. But it'll get there. The 3 columns that you see in the trace route are 3 different attempts. And it's giving you every address of every router along the way. In this case, they're IPv6 addresses. So what I see here is to connect to google.com, it first connects to the number 1 IPv6 address, and then it proceeds for each of those routers to contact their gateways at the level above, and you're giving the number of milliseconds for each respective test. At the very end, Google has Seattle 09 S30 X0E at 1E100.net as a server name. And that is the final server that serves my google.com. That's their domain name service, their content delivery net server. Now you can trace this route to anything you want. So here I'm going to try and connect to VFS and figure out what the route is, and we can kind of walk through it. Almost there. Now, you might look at this and go, what exactly did this tell me, Scott? What help was it? Well, I can tell you a bunch of stuff. First of all, the 192.168 address is my local router, my home router. The 5068.224 address, that must be my internet service provider, in this case Shaw. And Shaw Cable has a number of servers that it takes hops through to find its way out. But then we start coming back the other way, and we go through this weird cryptic set of servers before we get to an IP address, before we get to Rackspace. And in Rackspace, we see a bunch of Rackspace servers and market to mail. Now, what this tells me is that VFS.com is not hosted by a machine that VFS has physically on site. This tells me that VFS.com website is hosted on Rackspace. And I can see exactly which IP address it's connected to. And so we can find the route from one place to another using this kind of command. I also get a basic idea here of how long it would take to send information back and forth. If I just sum up each of the columns, I'll get the average amount of time it takes to get from one place to the next. So you can try routing. I would suggest try routing to some server or service that you're curious about and see how many hops it takes to get through. Let's try one. It's an interesting test to do from home as well to see whether there's a lot more hops getting from your home network out to certain services, or whether or not you can do that directly from your home network, or whether it's faster from VFS's network. Now, once you've given that a try, you'd be ready to start thinking about, how do I make two programs talk to each other? Now that I have an idea how the network works behind the scenes, what do I need to do to get two applications to talk to each other? So, conventional terminology, client and server. And the server is the thing that has information or a service that it's providing, and the client is the user of that information. We're going to try and set up some way that our client application can make a remote request to that server and get some information back. We typically do this because we want to have some remote capabilities. Sometimes it's storage on the server. Sometimes it's security. Sometimes it's interconnectivity. I want to connect multiple people together. I want a chat service. I want an online gaming service, and I want people to play in the same arenas. So we do that by creating a server or service that actually facilitates the functionality that we want. In an internet application, things kind of follow this basic flow. Our client takes some user data, it figures out the right protocol to send it and the IP address and port number to send it to. It then fires it off into the network adapter where those other layers of the protocol do their thing. It gets sent through the internet, and the network reroutes it to our server, where the network adapter on the server decomposes all the gobbledygook that got placed at the client end. Our protocol gets pulled apart, and finally our information gets delivered to our server. So we've got an IP address that identifies the machine. We got a port number that identifies what program is going to get connected. The rest of the story is told through the way we connect things. And the way we connect things is through what we call a socket. Now, if we were looking earlier at the file system that the operating system was taking care of, we allowed ourselves to have a file system that could create, edit, read, write, and destroy files. And the operating system took care of managing how the files were dealt with. You simply opened a file, it gave you a handle or a reference to that file, what we call a file descriptor. You would write bytes into the file until you're done, then you close the file and hand the file descriptor back to the operating system. And so the idea with sockets is kind of to do the same thing. We're going to open the socket, we're going to get the equivalent of a file descriptor, and we're going to read and write bytes into that file descriptor until we're done with it. Now, on the configuration side, on the machine that's doing the server, you have to configure which program to start when a certain port is trying to be accessed. But once that program is running, it listens on a socket. It listens on a port number. Everybody who tries to connect to that port number connects directly to that program. So if we were to equate this to the way the web servers work and the web services, which is the easiest way to think about it, your browser is the client. You've got a web server that's waiting for requests on port 8080. That's why we type in localhost or 127.0.0.1, which is the official IP address for the name localhost. And that address followed by port number 8080. 8080 is the de facto standard port we use for the web connections, the web servers. Your client, the browser, connects to that. And once they connect a socket between each other, they can now send information back and forth. So we use those ports to identify services. Now, each piece of information gets sent back and forth via those sockets. The next part we need to choose, and this is part we actually play with in our applications, is the protocol to send things. The datagram protocol is really lightweight. It's allowed to send messages up to 8 kilobytes. And of those messages, we don't provide any additional features. Means it's fast. On the other hand, TCP protocol allows us to send information of any size. It breaks it into 8 kilobyte chunks for us and shotguns it through the network. And when it breaks it into those 8 kilobyte chunks, it also numbers them. When all of the chunks are guaranteed to arrive back at the server, they are all reassembled in order, and then the application's told that the data is ready. Okay? Any packets that are lost are resent. So every packet that's sent has to be acknowledged that it was received. Now, that takes a little bit of extra time, but the value is that you're guaranteed that your information gets there, and it gets there all in one piece. Can you think of different reasons why we would use these two different protocols as we're building applications? When would we use a TCP protocol? Not really. The problem with the TCP side of things is it's slow by comparison. Right. So I would use a TCP connection when I'm logging in, because I can't do anything else until I've verified a user. I would use a TCP connection to update results or to pull down, say, map information. I can't play until I have the latest map or the latest layout. Okay. UDP I would use in-game, because when I'm in-game, I'm trying to run at 60 frames a second, which means I'm going to be firing packets probably every second or third frame. And if I miss 3 in a row, so what? I'm running at 60 frames a second. If I miss 3 packets, I might have missed 10 frames. That's 1/6 of a second. That moment has come and gone. And the fact that I missed a bunch of information, no big deal. And you've probably experienced this in a game. If you've ever played a game and you've been running along somewhere and all of a sudden you kind of just stopped, and then all of a sudden you skipped forward, that's a UDP packet loss. Right? Because you didn't get a bunch of packet updates sent out, so the server didn't update your position, and then all of a sudden another packet got through a few tenths of a second later, and you skipped forward a little bit because it got confirmed. The other thing is that with UDP data, we're sending messages, and there's no constraint on what we put in those messages. So if I want to inject my own sequencing numbers or my own validation stuff on my UDP packets, I'm perfectly capable of doing that. And this is part of what the network programming job in game developers is all about. 1, navigating routers. 2, navigating firewalls, so that you can play a game from behind a firewall to a server that's on the other side. And 3, figuring out what do I put inside the data and the datagrams to send to a remote server so that I can keep the nicest, smoothest gameplay possible and make it feel as fair as possible. At the same time, recognizing that at 60 frames a second, that means I'm doing a new frame every 16 milliseconds. and our networks don't run that fast. So that we need to throttle the speed at which we're sending things to our network server. Now it gets even more complicated if you're the network programmer on a game and you decide that you're going to make your game peer-to-peer network. That means every client is connected to every other client and there's no central server. Now there's an upside to that. The upside to that is the players pay for the bandwidth. The server doesn't. The players cross-check each other. If you're playing in a 30-player game and 29 people say you died and you didn't, I'm sorry, but you died. If the majority of people say one thing, that's the way it goes. So it's a little bit easier that way. The downside is if you got 30 players in a game and it's a peer-to-peer network, that means you don't just have to send one packet out to a server and the server broadcasts it back to everyone else. You have to send a packet to every client. You have to keep track of every IP address and go through them. How do we send that information? Well, really, we just think of them as files. Once you open a socket for reading or writing, you're just writing bytes to a file. And those socket handles you use in exactly the same way you would use a file handle or a file descriptor. As we go through the program, we are going to do some of this stuff where we actually open up a file and read and write stuff to it. Connection-wise, the server is going to sit and listen on a port number until a client asks for a connection. The server is going to accept that, and then once those two are connected, they can then send information both directions and talk to each other, quite literally. There's kind of what it looks like graphically. The server sets up a socket, it binds the socket to a port number, and it starts to listen and just sits there and waits. On the client side, you create a socket and you try and connect to an IP address and a port number. And once that connection is accepted, you can then send data to the server. The server, upon accepting the connection, starts receiving data. And it receives data into a buffer until you decide how you terminate that topic or that discussion. The server can also send information back to the client. And this is key, they're bidirectional. Now, when we do those low-level UDP datagrams, we've got things a little bit different. It's a little simpler to set up the send and the receive. But the information that goes inside becomes more of you as the programmer have to decide what to do. The picture for that looks a little simpler. It's kind of like this. So our server sets up a socket, it binds to a port number, and it just starts receiving data. Anything that gets sent to it, it just starts to flow into a buffer. On the client side, you create a socket, bind to your IP address and port number, and just start spewing data. And you just kind of let it flow. On the server side, you can send receipts back if you want. You don't have to. You don't have to acknowledge things at all. So we talked about this a little bit, UDP and TCP end up both being used in game applications. The TCP stuff is what the web uses to send information back and forth to a web server. The UDP information is very much faster, and it doesn't have as much overhead, but you don't have any guarantees, and you have a size limit on what you can send. The TCP stuff has no size limit on what it can send, and it guarantees the information will get there. Different problems require you to have different uses or different connections. So we can take a look at, in game, we're going to use both of those type of connections. Now, I'm going to suggest we're going to give this a little bit of a try. So the first thing you're going to need is you're going to need Visual Studio, and not Visual Studio Code because it's easier to write this as a C# application. But if you want to try and do it, we can try and put together a simple client server that just talks to each other. Then you're going to run them both, two separate terminals. You run the server in one terminal, it just sits there and listens. You run the client in another, it'll connect, send a message, disconnect, and exit. And so once you can start to get the idea of how you can get two programs to talk to each other, even if they're on the same machine, putting them on separate machines becomes pretty trivial. The operating system takes care of that part. So we're going to start, I'm going to see if I can share my Visual Studio. I'm going to try it. I haven't done this with 2022 yet. There we go. That should work. And let's put that in the text channel. Let's see if that'll work. So if you fire up Visual Studio 2022 and try and connect, you'll be able to see what I'm playing with here. In the meantime, here's my Visual Studio. Now, I'm going to create a new project. Just from the new menu, choose a new project. You won't see the dialog box, but you're just going to create a console application. I'm going to call it Net Client. And I got a simple little C# program. Now, I'm going to need a few pieces. So for my network client, I'm going to get rid of this stuff. I don't really need that. And I'm going to start in by creating my own namespace here. And in that namespace, I'm going to create a client. Actually, let's make that program really, really simple. We're going to make a program. Gotta spell it right. Okay. And for our main program, what are we going to do? Client. I'm going to make a new client. Not a client certification option, just a client. And then I'm going to tell that client to start. There we go. And it also means I'm going to need to have that client object as part of my program. So we're going to need using system. We're going to need networking. Sockets. These are the modules we're going to pull in. Now, I'm going to need another file here. Class. We're going to call it client. I don't think you see the pop-ups. It kind of sucks. You don't see the pop-ups in LiveShare, do you? Well, here's my client class. And I'm going to need let's just put that guy in there. Let's save that. There you go. Now, I am going to put together, what does my program do here? It tells my client to start. So I'm going to create a start method. And in my start method, I'm going to create some bytes to write. So, byte array. I'm using these really low-level data structures. And then what I'm going to do, I want that. IP host. I'm going to need the network stuff here as well. Get host entry, host name. So that's going to give me the host name I want to connect to. Now I'm just hard coding it at this point to localhost. I need an IP address. take the first item. So what that does is it uses the DNS library, which is part of the system.net library in our C#.net libraries, talking to the operating system to go and look up the host name localhost on the local computer and return it as an object. And then use that host to go get its IP address. Right? And then I'm going to have to connect a port number. So that remote port is an IP endpoint. We're going to use that IP address, and I'm just going to do a really bad thing and hardwire that in. Okay, so now I've looked up the host name localhost, and I've gotten its IP address, and I'm hardwiring port number 111,000. So now I'm going to create a socket. Now the socket is the connection to the server. Address family, socket type stream, protocol TCP. There we go. Command completion is great. Next thing, I'm going to try and connect to my remote port. And assuming I connect, I'm going to send myself a message just to put on the console locally. And then I'm going to send a message and receive a response. Just a little bit weird. I'm just going to send it as text. And we're going to try and send that to our server. Now that's going to take our text that I generated and it's going to turn it into a byte array. So the next thing I want to do is actually send it. And that's pretty much all there is to it. Now, I can go receive any response I get from the sender. So I collect the bytes sent and bytes received merely so that if I want to do some error checking, I can. And I need a buffer to put anything in that we receive. So that's what this buffer is for. In fact, what I should do, put that there. Right. Yeah, there might be a couple things yet. We don't have a server, so there's nothing to talk to. And if we have any errors, we're not managing it, and I'm not shutting down the socket yet. So let's close it up behind ourselves nice and neat. Okay. and then close it. Now, typically what I'll do is I'll wrap that up in a try-catch block. And a try-catch block is a very slow way to do things because nothing inside a try-catch block can ever get optimized in any language. However, when we're doing network communication, it kind of makes sense that we want to fail gracefully. So we're going to put that try-catch block in. Right? And the way we're going to manage it is we're going to catch some of these errors. And we're going to take the argument null exception. And if we find that, we're going to do something. And what else are we going to catch? Socket exception. Typically, you just put some sort of write line in each of these. And the last one I usually throw in is a generic exception. It's kind of the catch-all. And just put some error messages in, something like that. So that's kind of a basic client. Now, you can compile this, you can build it. Running it isn't going to do much because right now we don't have a server. So we need to start a whole new application to build the net server. I'm going to try and do that here. Hopefully it'll create it in a separate folder. New project, console app, next, net server. Yeah. So in this program, I'm going to do something similar to the client program. Now, the way this works is that once you build the server, you're going to build a socket connection, and that server you're going to start first. So you're going to compile it and build it, then you start the server, and then you start the client. The client connects to the server, the client sends a message to the server sends a response, they both shut down. Hopefully it just works. Let's do this name server. What curly bracket am I missing? Oh, I don't need that. And I don't want const static. Better. And then in here, We'll start up our server, and then it'll stop, and then we'll exit. So I'm going to create a new class. File, add. Class. Server.cs. Yay. Now a lot of this is going to be kind of similar. So I'm just going to copy it from the other instance. Take that host name. Localhost. And then we've got our start method again. And inside our start method, we've got the whole get host entry, get IP address, get local endpoint. It's almost identical to the client. And I'm going to put this one in a try right away. So again, we're going to choose a socket here, not an HTTP. Command completion sometimes. Could add system.net. There we go. So we've got the address family, socket type stream, and protocol type, TCP. So that's where you set the TCP versus UDP side of things. Sockets, socket. So here we go. And now what we're going to do on the server side is we're going to bind our listener to a port number. Let's call instead of the auto-generated name. Right. There's the listen port. And then we've got to specify how many requests we can accept before we die. Let's throw 10 in there for now. Great. And now what we're going to do is we're going to pop up a console message, and then we're just going to wait for connections. Oops. Listener accept. And then when we accept data, we're going to start to process it. I'm just going to make those empty. Done. Let's throw that in there. Just the classic way to end a loop. And now we're just going to receive some data. I'm just creating a buffer here. And then we're going to turn around and listen and bytes received. Receive into that buffer. And now we're going to do the reverse operation that we did on the client where we took a string and turned it into bytes. We're going to take the bytes and turn them back into string. ASCII get string bytes. There we go. We just have to tell it how many bytes to read. Then we're going to do some weird stuff here. We're going to take a look at the index, right, of that data, and we're going to look for the end of the file. And then we're going to get out. Now at that point we've received some data, so we probably want to spit it out on the screen. Right? And we probably want to shut down nice and clean at this point. And what I'm going to do is I'm going to send a response back to the client to tell it we're done. What are we pulling in? Well, let's just not datagram. I just want another buffer. What this? Oh, we'll use the same one. Sure. Same. I'm just reusing the same buffer. And then I'm going to shut it down. As much as possible, I'm trying to use the command completion in Visual Studio so that I get the names of the methods right. And of course, I can put the catch in here. Just dump whatever message was there. Yeah, but I want to throw a key press in there. All good. Now, in theory, I should be able to compile this, and it should run. And if I compile it and run it, I'm going to need a couple terminals, right? So I'm going to try and build this guy, see how broken it is. All sorts of broken. Byte array. Look at that, built okay. So then I got to go back and open the other project. That client. And I got to build it. Okay. And then we got to look up here. Networking. I've got my net client and my net server. I'm going to go in there and I'll see what Visual Studio built. Now the bin folder is what I'm really interested in. The object folder we know is intermediate. I'm going to create another terminal here. And in this terminal, I'm going to go into networking, net server. I got one in the server, one in the client, two separate folders, and net server, waiting for connections. Here, what is it? No, didn't build it. It says it succeeded, but it didn't build. Why didn't it build? Yeah. Oh, it's in the wrong folder. Init host entry. Not end. Did it work? Yeah. There, not very exciting, right? So, socket connected to server. The test message doesn't make it all the way across. You don't get it written out here. So now we have to get into running the debuggers, and that gets into a little bit more complex. When we start debugging this stuff, you need to run 2 copies of Visual Studio simultaneously and 2 debuggers simultaneously, which is a little hard to show on the screen here. I'll see if I can fix the simple little problem. We're going to take a short break for another 10 minutes here. And when we come back, we'll take a look at some of the things we can do with the network. All right?
also has information on the salesperson. So you also want to know how many lines are out of the yeah, the vector. So and then you also those individual cells to be set something. This case is what
So let's take a look at that quick example. We'll try and open it up to the whole screen there. Well, turn that off. Turn that off. Turn that off. Get the whole screen. No, you can't really read it, and that's okay. I'm okay with that right now. To debug these things, you notice I've got 2 full copies of Visual Studio up, and I've got breakpoints. I've got the server on the right hand side of the screen, and the client on the left hand side. Vice versa, depends on how you're looking at it. When I push run on them, I'm going to get a little output box there. I'm going to push run on this guy. I'm going to get an output box here. And they're going to stop to my breakpoints here. And then I'm just going to continue and wait for that connection. And you see it stops in the debugger here. As it stops in the debugger, you know, the biggest problem I had, this is looking for the specific text end of file. It's not something that's inherent in C# or the operating system or anything. It's something that in my source code, I need to actually put that end of file in the actual message I'm sending back and forth. When I turn around here and tell this guy to start stepping over things, I'm going to go receive these bytes. And I detect that end of file, so I say I'm done. Then I can see the output here. I'm waiting for my connection. I'm going to continue. And over here, I'm going to continue that one as well. And as they finish, you'll see the message got sent from one to the other. And then the client gets shut down. Now, it's kind of early days to be starting to play with low-level sockets and stuff like that. I just wanted you to see the idea that you're going to create a connection and you're going to send information between the 2 machines. The fact that they're on the same IP address is just a way of testing it quickly. When we're connecting our data together, the most important part really comes down to that part in the middle. And so when I zoom into it a little bit more, this guy here, when I zoom into it a little bit more, what we're really seeing in our debugger is this part here, the message I'm actually sending, is the most important part. The protocol or the way you send information. As we get more sophisticated, what we're going to do is not send a string back and forth, but we're going to create a data structure, literally in C#. And we're going to turn that structure into a collection of bytes and send those bytes back and forth. As we send them to the server, as long as we have the same class definition in the server, we can take those bytes and cast them back into an object of the right kind. And we'll get that data structure to be able to be sent as bytes back and forth. And this is how we actually send information back and forth between client and server in our applications. The next step after that is really, what do you want to do with that? And for the most part, though, what do you want to do with that question really comes down to what do you want to do with your server? I mean, if you're controlling both the client and the server, what's going on here? What was that? Not. No. There we go. There we go. Back to kind of normal. So as long as you get the idea that you can send information back and forth, that 90% of the work of routing from one place to another really has to do with letting the network do what the network does. That your choices are really whether you send UDP or TCP, and whether you send text strings or whether you send bytes of information. Everything after that comes down to exactly what do you want your server to do. And in most cases, we want our remote servers to do some sort of work for us. Sometimes we want them to do web type stuff. Sometimes we want them to use cloud services. We want to do computation. We want to do machine learning. We want to do storage. Sometimes we have large data sets and we want to have a common access to a common data set. We're going to move all of that out to a server. One of the most common uses for a network connection is for a relational database or an external database. And while relational databases are most common, they're not kind of what we're doing new these days. Most of the time we're doing to cloud-based data stores. But in either case, we're making a remote connection. Hopefully it's buried low level, and so that we just see an API or a library that says, connect me to this database, make a request to the database, give me some data back. Quite often with these data stores, what we want also is the ability to handle multiple connections simultaneously. We want somebody to have built the server for us and tested it for us so that tens of thousands of people can connect to that data store all at once. We want large chunks of data. One of the other things we can build is dedicated game servers. Whether it's a lobby server to be able to manage users and redirect them and load balance them across different game servers, or whether it's taking care of purchasing or item development, all of those things, maybe even some matchmaking or network play, could be done through a game server. And sometimes we're going to have to build our own game servers. That's a dedicated C# or C++ application that sits and listens for connections and pairs up multiple people. It's something that, you'd build something that created a list and said, hey, I can have 32 players. I'm going to make a list of 32 connections. I'm going to accept 32 connections on this port, and once 32 are filled, I'm not going to let another player in. And most of the time, game servers are simple redirection servers. That is, every player uploads their position and their heading and their velocity and the current action they're doing. And the server takes that information and it broadcasts it right back out again to all the other players. So I upload where I am to my server. The server collects from where you guys are and where I am, and then broadcast that out in one big chunk to me and to you and everyone else playing the game, so we get an update for where everybody is. Next term, we're going to start playing around with web servers. We're going to build our own web servers. We're going to build web servers that let us take textual information and send it and receive it to and from a remote computer. We're going to use this technology for doing a couple things. In the future, we're going to use it to talk to the cloud. We're also going to use it to build our own servers and services so that we can build specific APIs on how to do specific game level things. We'll build some technology and some tools around this. We're also going to take advantage of cloud servers. So we're going to use some services from either places like Google or Microsoft where we're going to acquire some storage that we can get for free, and we're going to take our application and we're going to upload information. We're going to use that information through a web application to analyze the information offline on the server and then pull it down in a nice graphical format into a web browser where we can look at it and analyze it. And this is commonly referred to as a telemetry type application. And most modern games these days have a lot of all of these things going on simultaneously. So there's a lot of networking in what we're doing. Now, I know that's a little bit of a dry topic for the day, but having a good idea what we can do with networks and distributed computing is kind of a prerequisite before we start building any of the actual stuff in the future. You probably won't see a lot of socket-based network construction in the future. Most of this stuff is managed through tools and libraries that are already built for you. But understanding what they do under the hood and how they operate is key to getting the most out of them. So that should be enough for today. As you can tell, my voice is gone. If you want, I can post the client and the server code onto Moodle, and you can have a look at it if you haven't been able to get it running yourselves. And you'd like that? Okay. Yeah, I'll do that. It's no problem. Okay, that just gives you a sample of what it kind of looks like. All right. Other than that, you're good to go. Ask David all your Minesweeper questions. He loves answering those questions. And we're good for today. And we'll see you guys Friday.